for the next problem on transistor circuits. So this video will help us in understanding what is bipolar junction transistor, its common base configuration, and one problem we will try to solve based on the common base configuration of bipolar junction transistor. Before we understand the common base configuration of bipolar junction transistor, let us understand the different transistor symbols and what are the different types of transistors available with respect to bipolar junction transistor. A transistor consists of two PN junctions formed by sandwiching either P-type or N-type semiconductor between a pair of opposite types. Accordingly, in a bipolar junction transistor, there are two types of transistors. One is NPN transistor and the other one is PNP transistor. An NPN transistor is composed of two N-type semiconductors separated by a thin section of this type, P-type. However, a PNP transistor is formed by two P-type semiconductors separated by a thin section of N-type semiconductor. So one important factor to be observed in either NPN or PNP transistor is we have the formation of two PN junctions. There is one PN junction here and the other PN junction here. So which means a transistor in general, it is considered as a combination of two diodes that are connected back to back. And here you can see that there are three different terminals where from each doped semiconductor type, there is one terminal that is considered. So here we have three sections of doped semiconductor. So the section on one side we call it as emitter, and the section on the opposite side we call it as collector, and the middle section is called the base, and that forms two junctions between the emitter and the collector. So emitter is the section where it supplies the charge carriers, and therefore it is called as the emitter. And collector is where it receives all the charge carriers. It collects the charges and its function is to remove the charges from its junction with the base. Base is the middle section which forms the two PN junctions as I told earlier, and you can observe here that when we consider in general as an NPN transistor or as a PNP transistor, you can very well observe that the base emitter junction is forward bias, which allows low resistance path for the emitter circuit, and the base collector junction, which is denoted as CB, the base collector junction is mostly reverse biased and it is going to provide you a high resistance path in the collector end. And some facts that we need to understand with respect to BJT is we have understood that there are three regions. One is emitter, base and collector, and the base is much thinner than the emitter while collector is wider than both the base and the emitter. Only for the sake of convenience of drawing, we just draw all emitter, base and collector as equally sized. Okay, but usually base is little thinner when compared to emitter and collector is wider than base and the emitter. The emitter is heavily doped so that it is a section where it is going to supply the charge carrier. So therefore emitter is heavily doped so that it can inject a large number of charge carriers, either electrons or holes, into the base. The base is lightly doped and it is also very thin. So it passes most of the electrons or the holes, the injected charge carriers, into the collector, and the collector is moderately doped. If the emitter is P-type, then the majority charge carriers that are injected into the base will be holes, and if the emitter is N-type, the majority charge carriers will be electrons that are injected into the base. And during the transistor operation, much heat is produced at the collector junction because the collector base junction that we consider is going to be a reverse bias junction, and therefore the collector is made larger to dissipate the heat. So you can see here at the bottom, I have given the transistor symbols. Note that the emitter is shown by an arrow, which indicates the direction of conventional current flow with the forward bias. For NPN connection, it is clear that the conventional current flow is out of the emitter as indicated by the outgoing arrow. Similarly, for the PNP connection, the conventional current flow is into the emitter, which is indicated by the inward arrow. Now to understand the transistor action, The emitter base junction of a transistor is forward biased here as indicated, whereas the collector base junction, you can see here the p-type is connected to the negative terminal of the battery and n-type is connected to the positive terminal of the battery. So therefore the collector base junction is reverse biased, and if for a moment if you imagine or if you ignore the presence of emitter base junction, then practically no current would flow in the collector circuit because of the reverse bias junction. However, if the emitter base junction is also present, then forward bias on it causes the emitter current to flow. It is seen that this emitter current almost entirely flows into the collector circuit because of the thin region of base and lightly doped base region. Therefore, the current in the collector circuit depends purely on the emitter current. If the emitter current is zero, then the collector current is nearly zero. Now we shall discuss with respect to the working principle of just the NPN transistor alone. So here this figure is the NPN transistor with forward bias to the emitter base junction and reverse bias to the collector base junction. The forward bias causes the electrons in the n-type emitter to flow towards the base. You can see here the conventional current flow is given in this direction out of the emitter. So therefore it is understood that the conventional current flow is going to be in opposite to the movement of charge carriers. So therefore the emitter is supplying the majority electrons towards the base, and therefore the emitter current is shown with outward arrow. Now the forward bias, which is causing the electrons in the n-type emitter to flow towards the base, this constitutes the emitter current IE. As these electrons flow through the p-type base, they tend to combine with the holes that are present inside the base. As the base is lightly doped and very thin, therefore only a few electrons, just less than 5%, combine with holes to constitute the base current IB, and then the remaining more than 95% of the electrons, they cross over into the collector region to constitute the collector current called IC. So in this way, almost the entire emitter current flows in the collector circuit. It is clear that the emitter current is going to be the sum of the collector and the base currents, because you can see here the emitter current is moving outwards the junction PN junction, but IB current is moving into the device and IC is also moving into the device. It is flowing into the device. So as per Kirchhoff's current law, we know that the sum of currents entering the junction should be equal to the sum of currents leaving the junction. Therefore, IE is equal to IB plus IC. So all these equations I'll be giving it at the end when we try to solve a problem based on the common base connection. Before we move very specifically to discuss about the common base configuration of the BJT or the NPN transistor, there are actually three leads in the transistor that we know that. One is the emitter, base and the collector terminals. Okay. So however, when a transistor is to be connected in a circuit, we require actually 4 terminals, 2 for the input and 2 for the output. This difficulty is overcome by making one terminal of the transistor common to both input and output terminals. So therefore the input is fed between this common terminal and one of the other 2 terminals. So the output is obtained between the common terminal and the remaining terminal. So accordingly, a transistor can be connected in the circuit in 3 different ways. One is the common base connection by having the base to be common between the emitter and the collector terminal. So which means whatever I say common, that represents that particular terminal is going to be grounded. So similarly, we can also have possibility of common emitter connection and common collector connection. So each circuit connection has specific advantages and disadvantages. So it may be noted here that regardless of the circuit connection, the emitter is always forward bias while the collector is always reverse bias. So now to discuss with the common base configuration. In this circuit arrangement, you can see here that the input signal is applied between the emitter and the base terminal, and the output is taken from the collector and the base. So here the base of the transistor is common to both input and the output circuits, and hence the name is represented as common base connection. And you can see here the common base NPN transistor is shown. Now we will discuss some parameters that are related to the common base configuration, and the first parameter that is taken for consideration is the current amplification factor, which is denoted by alpha, which is the ratio of output current to the input current. So in the common base connection, the input current is the emitter current and the output current is the collector current. The ratio of change in the collector current to the change in the emitter current at constant collector to base voltage is known as the current amplification factor. This current amplification factor will be less than unity, and this value can be increased but not more than unity by decreasing the base current. So therefore, by decreasing the base current, alpha can be increased but within unity. So this is achieved by making the base thin and doping it very lightly, and the practical values of alpha in any commercial transistors will range between 0.9 to 0.99. And if only DC values are considered without any change in the current, then alpha will become IC by IE. The second parameter that we are interested in is to obtain the total collector current expression. The whole of emitter current does not reach the collector because there is some recombination that is happening at the base region, and it is because of a small percentage of it as a result of electron hole combinations that is occurring in the base area that gives to a small base current. Moreover, as the collector base junction is reverse biased, there is some possibility for this leakage current also to happen due to the minority charge carriers. So, the total collector current consists of two components. One is the portion of emitter current reaching the collector terminal, and the other one is the leakage current, I leakage, which is the current due to the movement of minority charge carriers across the base to collector junction on account of being reverse bias. So this is generally much smaller than alpha times IE. So therefore the total collector current becomes IC is equal to alpha times IE plus the I leakage current. And it is clear that if IE is going to be 0, which means if my IE is 0, if I assume that is emitter circuit, if you are going to consider to be an open circuit, then a small leakage current still flows in the collector circuit because of the reverse biased connection. So this I leakage is also abbreviated in some textbooks as ICBO because of the collector to base reverse bias junction. There is a leakage current. So therefore this means ICBO is the collector base current with emitter open. This O is representing open emitter circuit. So therefore my IC equation will be rewritten as IC equal to alpha times IE plus ICBO, and we know that emitter current is the total collector current plus the 5% recombination that happened in the base. So that is constituting to IB, and therefore this, if we substitute it in the first equation, IC, this will become IC is equal to alpha times IC plus IB plus ICBO, which is the leakage current. And therefore, if you bring IC, the common terms, to one side, this will become IC into 1 minus alpha equal to alpha times IB plus ICBO. So therefore, my IC, the final expression will look like this: alpha by 1 minus alpha times IB plus ICBO divided by 1 minus alpha. Now, these two relations, which are marked as 1 and 2, can be used to find out the collector current IC. And it is also clear from these relations that the collector current of a transistor can be controlled by either the emitter current or the base current. Now, let us solve one problem related to the common base circuit configuration of NPN transistor. So, the question here is, for the common base circuit which is shown in the figure, we have to determine the collector current IC and VCB, which is the collector to base voltage, and we have to assume that the transistor is to be of silicon, and the given data says The emitter resistance Re is given, collector resistance Rc is given, VEE is 5 volts and VCC is 20 volts. And we know that the transistor is of silicon, so therefore the voltage VBE will be 0.7. And once you apply KVL at the emitter side, the equation will become, because we have VE here, so starting from this, we'll also have IE into RE. And at this junction, this is a PN junction where we have this base here, which is connected to the ground, and we have the emitter here. So there is VBE drop across this PN junction. So when we write the KVL at the emitter side loop, we'll be getting VEE equal to IERE plus VB. So sum of all the voltage drop around that loop should be 0. So therefore, if you write VEE minus IERE minus VB equal to 0, so therefore I have rewritten it as VEE equal to IERE plus VBE. Therefore, emitter current IE will be equal to VEE minus VBE divided by I. So VEE we know it is 5 volt minus 0.7 divided by 1.5 kilo ohms. This will give us 2.866 milliamps of emitter current. And we know that IC is almost equivalent to IE, because we know that most of the emitter current will reach the collector side only because of the lightly doped base region. There is going to be only a 5% of the current that is going to be constituted by the base, and here that too in a common base configuration, most of the emitter current is equal to the collector current. So therefore we can just equate IC is equivalent to IE. Now applying KVL at the collector end, we'll be having VCC, because we need to start from here. This is the collector side loop. So VCC minus ICRC minus collector to base voltage. So this is because this is a PN junction, right? So here we'll be having another VCB. Now this VCB only we need to find out. So therefore we write the equation here as VCC equal to ICRC plus VCB, which is VCB equal to VCC minus IC into RC. Now we have all the values of VCC, IC and RC. VCC is 20 minus 2.866 milliamps into RC is 1.2 kiloamps. So kiloamps and milliamps gets cancelled. So therefore we'll be having VCB as 20 minus 3.44, which will be 16.56 volts. So here we have found out what is IC and VCB as per the given question. So this is the procedure to solve any common base connection in an NPN transistor. Hope you all have understood about what is a bipolar junction transistor, what are the different types of transistors available with respect to NPN and PNP configuration, and then we also know about the different symbols for NPN and PNP configuration. And we have also seen that there are 3 different terminals and what are the characteristics for each and every terminals associated with the bipolar junction transistor. And we have also seen with respect to the 3 leads of this bipolar junction transistor, we have 3 different configurations, right from common base, common emitter and common collector configurations. And here in this video, we have specifically seen what is common base connection, what are the parameters that are related to common base connection, and we have solved one problem related to common base configuration of NPN transistor. We will continue to solve some more problems related to BJT transistor. Until then, stay safe. Thanks for watching this video through Electronics Insight channel.